All right, so I just updated and added some filters to change the contrast on the screen. I hope that looks a little better for the paper. So let's start this all over. We're going to do example problem 2-11. Add a point in a structural member subjected to plane stress, 2D stress. There are normal and shearing stresses on the horizontal and vertical planes through the point as shown in the element figure 235. So there you see that right above in the textbook, it's to the side. Determine the principal stresses and the maximum shearing stress at the point. So I started writing down because I had actually started to do this in another video, but I didn't like the lighting. So find the principal stresses, and then B, locate the planes on which they act and show the stresses. So find theta and then show the stresses. And then sketch a triangular element showing the principal stresses and the maximum shearing stress and the associated normal stress. So there's a little bit more drawing, but really we're looking at stress transformation equations again. We're doing the same thing. So let's start working on it. I think what I'll do, I'm going to move this over here, and I'm going to shrink it. Well, I'm going to shrink it to right there. We don't need to see it all. And oh, look at that. I'm not moving. Huh. Let me pause that and see if I can fix it. Not that we care too much. All right, got that camera working for whatever value it adds. So we're going to start though with our drawing, and we're going to start with, here's our situation. We've got that stress cube, and I've got these stresses given us. So I've got 8,000, and I'm going to label this whole thing as PSI. Well, it's all in PSI, so 10,000, and I've got a negative shear of 4,000 PSI. Sorry, yeah, PSI, yep. I'm going to write this out the way I've encouraged you to, that this is the normal stress in the x direction is equal to, it's in tension, so it's a positive 10,000 PSI. And I'm going to put a little note, all units are PSI. Sigma y is equal to a negative 8,000. It's in compression. It's in compression, or we could look at the figure on the screen. And lastly, tau xy, that's a negative 4,000. All right, we're ready to start. We're ready to start. Once we have that, right? So our first question is find our principal stresses. Well, I can find our principal stresses. We simply have to plug them into that principal stress equation. Oh, sorry, I got to get rid of that. And I got to fire up this button, which is, there's my principal stress equation. So equation 215, while you're looking at it on the screen, I'm going to copy it down. But realistically, that printed version is probably a little bit more easier to read than mine is. So that equation is the principal stresses, there's a maximum and a minimum, are equal to the average of the normal stresses, and then plus or minus an amount, which is the square root of the difference in the difference in the normal stresses divided by 2 squared. So when I say difference, I don't have to say x minus y, because if I do y minus x, it would have a sign issue, but then I square it and it would go away. So it could be x minus y or y minus x. It doesn't matter which direction you're looking at. Plus the shear in the xy squared. All right. Mine looks like that. Yeah, I know, a little sloppier. Now, a lot of you are going to be inclined to punch in all the numbers and solve all of that. I'm going to give you a trick that just seems to make sense. If we write down our second equation, which is the shear equation, the principal shear, that's equal to plus or minus this term under the radical, right? This is this. Draw it here. Let's get another pen. Can't use turquoise when I'm using blue. This term is this right here. So I often will solve this I'll solve this term because then when I get an answer, I can drop it in there. And then this equation becomes the normal stress in the x direction plus the normal stress in the y direction divided by 2. The average normal stress plus or minus tau max. Sorry, I was writing tau xy, but it's tau max or tau principal. Let's put a P there for principal stress. All right, so principal stress is equal to sigma x 10,000 minus a negative 8,000 divided by 2 I squared it, put the radical, plus the shear stress squared minus 4,000 squared, right? If I do all of that, let's get a new piece of paper out. I already labeled the corner on this one. I already labeled the corner. Example 211, page 2. 10,000 minus 8,000 divided by 2, that's 9,000. Tau principal equals 9,000 squared plus minus 4,000 squared equals, and the answer for that is 9,850. And PSI, same units, see above. But now that I've got that, now I can go back to tau principal 1, or sorry, tau. The normal stresses that I've got are equal to sigma x plus sigma y divided by 2 plus or minus 9,850. Well, that average is 9,000, right? Equals, I mean, we can punch that in. It's going to be, let's do, oh, sorry, it's not going to be 8. Oh, see, that's why you got to write this stuff out. This is 10,000 plus or minus 8,000 over 2 plus or minus 9850. And so that's going to be 2,000 divided by 2 equals 1,000 plus or minus 9850. All right, now we add answers. Yeah, I've got 10,850. That's one answer, PSI, and that's going to be in tension. And then the other answer is 8,850, and that's also in tension. No, I'm sorry, that's not. That's negative. Negative. That's in compression. The signs will tell you that. So tension compression. Okay. That next task, I knocked off this first one. Take my green pen because I just love Michelle for getting me those pens. Take those pens. Take those. The next one, find theta and show the stresses. Theta actually isn't a challenging one. Well, honestly, we've got some really good math skills. So understanding where to plug stuff in, and really starting with this and converting it, getting the conversion process from this over to that is really the hard part of these problems in terms of punching the numbers. Understanding all of this and using it is, that's the next level, but that's good. So find theta. Find theta. Well, the equation for theta, let's pull that up on the screen. I don't have an equation for theta, but I do have that equation 214. Tangent of 2 theta is equal to 2 tau xy over sigma x minus sigma y. That is, it's well, we're going to see where that equation comes from. I'll spend more time on that in a lecture part, not in a homework part. Let's just use the equation. I punched that in there, and now we've got 2 times tau xy. I got to go back to my sheet. Tau xy is minus 4,000, so it's equal to 2 times minus 4,000, and then divided by, and that's x minus y, so this is 10,000 minus negative 8,000. 10, I'll put the zeros down, minus 8 negative is equal to minus 8,000 over 18,000. Really time to start dropping a lot of zeros. Start using K. Just use K for kilo PSI. All right. When I do that, now that's tangent of 2 theta, so we're gonna calculate that out. This is gonna be I'm gonna leave that alone. Actually, there's a trick here. This is going to be equal to, if I drop the zeros, that's going to be equal to negative 4/9, right? I just divided top and bottom. And then in your head, you should remember that trick from negative. You should remember that trick from school. 4/9, those are going to be a repeating decimal. All right. All right. I'm going to shrink this figure up since I'm actually using that space now. And I'll slide a little bit away from the edge. Okay. That's that. That's tangent of 2 theta is equal to minus 0.44, and then however long you want to go. And so then if you do the inverse tangent, you get, and I'm going to do this in a couple steps, 2 theta is equal to a negative 24 degrees. It's actually 23.9, but negative 24 degrees. Theta is equal to negative 12 degrees. Negative 12 degrees. Okay. So let's start looking at that. Is that the next part of my problem? It sure is. Show the stresses. Show the stresses. All right, so let's start drawing this out. Let's start with a coordinate system. So we've got a frame of reference. I've got my x and my y axes. And now we solved that principal axis was at, or that theta value. And actually what I kind of shortchanged on is there's going to be two values really that this occurs at. But the one that we solve for, the one that's going to pop out of the calculator, is at this minus 12 degrees. And this is going to be one of our principal axes. Now, we're also going to have another principal axis, and that would be, if we think about that tangent, I'm showing you a sine and a cosine, but if we think about a tangent, 180 degrees away, we're going to get the same value. So this value could be minus 24, or it could be 156, and then that gives us, this is theta 1, and here's theta 2, which is now equal to 75 plus 3, 78 degrees. All right, 78 degrees, well, that makes a lot of sense, because 78 degrees plus the 12 gives me 90 degrees, and that says that my principal planes, where these principal stresses occur, are 90 degrees apart. That's where I'm going to get the peak stresses. So that's kind of what we saw coming out of the math. That's what we solved for here. So it's good that we're repeating that. All right. So I don't know what that stress is though at minus 12, because we didn't solve for that. We solved for, that's the location and its value. I know that sigma P1 and sigma P2 are, and I got to look back at my numbers, 10,850 and negative 8,850 equal to either 10,850 or negative 8,850. It's one of those two values, but I don't know which one. I got a really good guess, but I've been doing these problems a while. So, and you, at the end of the chapter, when we do Moore's circle, you might have a really good guess for this too. So how would we do that? Well, we could go back, and I don't have the equation sitting in front of me. I mean, it's in my head. It's not on this screen. It's from the previous section, and that equation is that the stress in an arbitrary direction n is equal to sigma x cosine squared theta, right? Remember, now you remember? Plus sigma y sine squared theta, that's my second term, plus 2 tau xy sine theta cosine theta, right? Actually, from our example problem, this is just sitting next to me. I just saw it. Example problem 2.8. There's our equation, but I wrote it down. So now we pop in theta equals negative 12, and out of that equation, we're going to get that sigma n is equal to our 10,850. Well, it's going to be approximately. It's going to give me some errors because it's 11 point. But that's, so now I know which one it is. When I go down here, this is equal to 10,850, and that's in tension. Get my hand out of the way. And this one is minus 8850 in compression. All right, now we want to draw a stress cube. So we started out with, you know what? I'm going to a new page. I'm going to a new page, and that means pause. So I'm drawing my stress cube. I started out with this stress cube, and it's the one shown on the side, right? I've got 8,000, and I'm in tension for 10, and I've got a shear stress for 4, negative 4,000. And now I'm going to get to this rotated system just slightly. There, I've got a rotated system. And at this angle, that's going to be my 10,850 in tension. And this is going to be my, I'm going to list it as negative, but it's, so now I'm kind of redundant that I'm negative, but you got it. 8,850. And how much shear is on those faces? None. None. Because that's the principal orientation. So now the next question that we were asked, the next question we had to solve is, or problem is, locate the planes and show the stresses on the planes in which they act, but then sketch a triangular sketch element showing the principal stresses and the maximum shearing stress. So they want us to draw this. Got to draw it right. So this is, well, it's supposed to be, that is clearly not 12 degrees, it's more like 30, but play along. And this face has 10,850, and this face has 8,850, and I didn't do it redundant. I'm going to put negative. I know it's. I'll label this. This is tension. That's compression, and then I've got a shear that I calculated and I forgot. I think it was 9,000. Boom, boom, boom. Is that on page 2? No. Yeah, it was. Sorry, might have even been on page 1. Page 2, 9,850. So that shear is going to act, I have to think about whether that is acting that direction or the other direction, but it's 9,850 PSI. That shear was, see, it's plus or minus, and that's because if I drew this the other way, if I drew this same stress cube, but now drew it this way, so now this is my X face, this is principal 1. This shear goes the other way on that face. So that's what I don't worry about the sign on my shear. I don't worry about the sign on my shear. Because if I look at this face, it goes this direction. If I look at that face, it goes, yeah, it works out. It works out. And tension failures are a lot different than compression failures. So we need to track that. So there's our problem, finished up in 4 pages. So I'm going to go back and label these. This is page 2 of 4. Now I know to put this page in the middle, 3 of 4. I hope that answers any of the questions you got on that one. And it shows us how to move forward and make our plots. All right, take care.